All right, here's a continuation of Class 17, and we're doing example 3. This again is another really long example, and this time though I do have it as as images from a previously laid out solution that I wrote electronically, because it was a homework problem years ago at the Coast Guard Academy. So this is problem 15.121 in one of the versions of the textbooks. I'm not sure which one. It's been a while. So this is a 2-cylinder air compressor that has two pistons within their cylinders riding on the same crankshaft. So they have these connecting rods, BD and BE, and they're each 190 millimeters long. And AB, which is the crankshaft, rotates about a fixed point A with a constant angular velocity of 1500 RPM clockwise. All right, so it's moving, boom, 1500 millimeters clockwise, and so the pistons are going up and down. Determine the acceleration of each piston when theta is equal to 0. This always annoys me because they gave you a figure that's got some interesting things going on, and then they give you the theta is equal to 0. So one of our very first things that we need to do is to figure out the geometry. A nice thing to get out of the way is to turn 1500 revolutions per minute to 2 pi radians per revolution and 60 seconds per minute, and you will get 157.1 radians per second. So you convert it. So the first thing I did was to redraw this thing into the configuration. This is what they mean when they say theta is equal to 0. That means that A and B are lined up with each other. A and B is lined up with B and D, and then we have a triangle that's formed by the BE crankshaft, connecting rod, and the crankshaft and the center line for the cylinder. We could find that angle right there, beta, right here, by taking that 50 and taking the inverse sine of 50 divided by the hypotenuse right here. So now we're able to find 15.26, which I think was a number from a previous example. All right, so we want to find the velocity and acceleration of point B to start with. In this, we're given the constant angular velocity, omega AB, so we're able to find, that's clockwise, so we're able to find what VB is going to be equal to. So that's just that angular velocity that we just turned into right here into radians per second times its distance, and I turned it into meters per second instead of going for millimeters. We also know that the tangential of acceleration is 0 because this was a constant angular velocity. We can find the normal acceleration at B by omega AB squared times the length of the crankshaft, or also we could call that the relative position of B with respect to A. And so that's omega squared times R, and we're able to find what that acceleration is of 1,234 meters per second squared. And already you could say, I'm glad we turned it into meters, because otherwise we have like 1,234,000 millimeters per second squared. That's just a big number. Who wants to do that? I don't. And so we would perform a velocity analysis on the connecting rod BD. So BD, perform a velocity analysis right here. Why did I do that? Well, what I'm essentially saying here, the reason why I'm drawing this thing in that way is that D is at the peak. It can't move up any higher or than it is right now in this position, right? We see it up here. D can't go up any higher, so he's going to start traveling downwards. So his velocity is actually going to be equal to 0 right now. Another way that we could also look at it, though, if we had drawn this out, sometimes looking at something that's pre-written out, it's hard to see, so it's the act of drawing that makes it make a little bit more sense. Its velocity can only come up and down, right? So the line perpendicular to its velocity, which I usually draw as a dashed line, it goes out this way. But then if we draw the velocity that's right here that we happen to know from VB, it's the line perpendicular to it comes right here. So that this right here ends up being, D itself ends up being the ICR. So it's actually rotating about that point. That's how we've convinced ourselves that it is rotating about D. And so from inspection, we say this right here. And so we could find from the velocity of B right here that we know, and now we know this B with respect to D is going to be the length this of BD. We're able to find the omega BD right here, and we're able to find its velocity, angular velocity. And then we could do an acceleration analysis of BD now that we know this. We know that AD has to move in a straight line position. It can't go to the left or the right. And we already have the acceleration of B, which happened to be the normal acceleration of this crankshaft right here. So we write out the equation for this top point, the point that we want to find, and we pin it about that reference B. And in the N direction, I decided to go N and T instead of X and Y. It just makes sense. Everything's aligned with it, so it's a much cleaner. So in the N direction, we say this is the velocity, the acceleration of D. And we have the acceleration of B that we know here, but we're also going to have this acceleration right here. For one thing, from inspection, we could also say that the tangential one is going to be equal to 0 because it just can't accelerate through the cylinder wall. So this guy right here is definitely pointing towards the center right here. So we have A plus this guy right here, and what we're going to end up finding is that, yes, definitely it is accelerating downwards, which actually kind of makes sense because, like I said, this thing was at its top. It couldn't go any further upwards, so it must need to accelerate downwards. Also, its velocity was 0, so it needs to be have some velocity at a later time, so it is accelerating downwards. So we end up finding this value for the acceleration. And it happens to be at a 45-degree angle because from the original we saw that these were 90 apart. So that's how that works. Now we go for the other part of it, finding the acceleration of the piston E. We do perform a velocity analysis on the connecting rod. We already did a velocity analysis of the crankshaft right here, so we could do it for BE now. And you'll notice that these velocities are in line with each other. And if you remember anything about that, that means that if we tried to draw an ICR, it would be infinite, right? That these two parallel lines would never cross each other, and therefore they would have they must be in pure translation. So the angular velocity of the crankshaft of the connecting rod happens to be 0. So it's very similar to that other problem that we did not long ago, where the connecting rod is kind of floating in one position. It's just making the transition of rotating with one angular velocity in one direction, and now an instant later it's going to be rotating with an angular velocity in the other direction. But at this instant, it's in pure translation. The acceleration, it's analysis right here of that BE. We draw these 3 diagrams, and it's convenient to align with the path of the coordinate system with the path of the piston, right? So I decided to make it this y prime instead of doing that tangent normal. So not in line with the connecting rod, but instead the coordinate system is in line with the line drawn from A through E right there. And we know the acceleration of B. We were given that. Remember back up from here, we've got that acceleration in the normal direction. So now we apply it to here. And we don't know the acceleration of E. It's the thing we're trying to find. But we do know its sense. We know that it's either up or it's down along this line of the cylinder. So we write out the equation for E. And we place B right here, the known one here. It's to represent the translation. We pin it at B. And then we put in the tangential and the normal accelerations on the end. And we already know that the normal is going to be equal to 0 because it has no omega. That makes it a little bit of an easier problem. So in the x direction, working through this right here, we find, okay, so, and by the way, it's the x prime direction, I should say, because that's going to be convenient for us. It's 0 right here. That's why it's convenient to align the coordinate system with use a strategy, not to just blindly go x's and y's. Because what you'll end up doing, if you do choose a different coordinate system, what you'll find is that you're going to have to have like simultaneous solutions of equations. But by aligning your coordinate system with some strategy, you're able to avoid that. So that's what we've done here, and we have this bx prime that's 1234 is what we find to be right there. Yes, because that is completely in the x prime direction. That's also useful to us. And now all we need to do is get the tangential component, turn that component of the components, right? The tangential component, the x prime component of the tangential component right here. And that means that we're going to take this cosine of that 15.26 degrees. And it's got to be a negative right here to be able to work out, right? Because this guy is in the positive direction, and this has to be 0, so it must be in the negative direction to be able to make this guy 0. And we're able to find what that tangential component is. And once we know what that tangential component is, we're able to figure out what the acceleration of E was. Now, what I did, I skipped a step here, something that we might have tried to do. I never found alpha of my BE. So this was sort of a little trick. I didn't have to find it. I just kept it as a thing where I'm going E with respect to B. I just kept that all as a single term right there. So I didn't bother to solve for it. I maybe skipped an itty-bitty step by doing it, but then I could just put it back down in there, and I could find what my angular what my acceleration is. So that's the acceleration, and we did find that it was positive, and so it is accelerating upwards, whereas over onto this guy over here, he's accelerating downwards. All right, so that's that problem. We're going to do another. This is going to be a next example. And do I have these open right now? I don't know. Actually, I don't know if I know. Yeah, I do. I know what this problem number is. So let me see. This is 15121. I have a feeling that it's not going to be in the same. It's not going to be in this edition. 121. Well, there it is, right there. Oh, well, no, this is 122. So this is a different problem, and they had 1500 RPM, so I think everything else is the same, right? So here's what the book's solution manual said to do. Once again, these are written by graduate students, and they didn't try very hard with their diagrams. I think they're written by graduate students. But anyway, This is a technique that they use sometimes in some of the editions where they actually leave these angles here inside these brackets. I really didn't like this method of writing these things out right here. But they're not using the 3-diagram method, which I find strange because that's how the book's examples run through. So the way that we use in class, and I show you to do, is the way that the book does their examples, and what I think is a preferred way. But then the solution manual proceeds to do it in this odd kind of form. But you could see, I think they get a different answer than us. Did they get a different answer? I forget. What did I say on here when we get the answers? All right, what did we end up getting? 1560, and we got 337. Yeah, okay, so that sounds the same. All right, that's the same. 337, 1558. Yep. So they got the same thing. But you can see that they are doing it in a different direction, a different method, which I think that ain't fair. That ain't right. So that was a 15-minute 15-minute thing. So let's be done with this and move on to another problem. Kaboom.